So hopefully we've gotten fairly comfortable with finding relative extrema by this point, especially since we're really just kind of repeating some of the same work that we were doing in the previous section. But the next thing we want to do is use those same ideas to look for absolute extrema. The problem here is that we do need to be really careful. Absolute extrema for a function may not exist in general. Let's think of a function. F of x is just a line, 5x plus 2. If we go ahead and sketch this, it's something like this. This line has no maximum or minimum point. I can keep going as far as I want, put in bigger and bigger values of x, and I can get bigger and bigger values of the function. Same thing with putting in smaller values and getting smaller values of the function. So this function on the entire real line does not have a maximum or minimum, an absolute maximum or minimum. The only way that we're going to get either one of those is by only looking at part of the line. Just look at a segment. Maybe I restrict my attention from 0 to 1. Going from 0 to 1, I essentially cut out a section of my line and only look at that section. On that section, there is definitely a minimum of 2 at x equals 0 and a maximum of 7 at x equals 1. This is definitely the highest point on that line segment. Now, restricting to an interval did help us here, but even that won't always work. Let's look at another function. Say f of x is equal to 1 over x. If we look at this function, draw a sketch of this one, we'll go ahead and actually restrict our attention back to 1 to 0, or sorry, from 0 to 1. Of course, here 0 is not actually part of the function, so we'll go ahead and look on the interval from 0 to 1, not including 0 this time. So we have kind of an open circle there and a closed circle there. This is a 1. So here we're looking at this section of our graph. Now there is an absolute minimum at 1. It is at its lowest point, but there is no absolute maximum. This function continues to go higher and higher as we get closer and closer to 0. So what we're going to have to find is some sort of condition that's going to guarantee that we do have an absolute extrema. That's going to have to somehow restrict our attention to cases sort of like this one, where we restricted our first function to 0 to 1, but not the entire real line. And on here, actually make sure that we don't have a place where we have an asymptote. All those need to be excluded. What we have is what we call the extreme value theorem. This name might sound kind of familiar. We discussed a similar kind of a theorem. It's called the intermediate value theorem back in chapter 1. That's actually the second of a collection of so-called value theorems. There's a third one called the mean value theorem, which I don't believe we're going to discuss in this course. But the extreme value theorem is kind of really handy. This says if f is continuous on a closed interval AB, then f has an absolute, max, and an absolute min on this interval. So there's two key pieces to this. First, we have to be on a closed interval. So we need an interval that looks like a to b. This excludes something like here where we were from 0 to 1. Not including that endpoint was actually kind of a problem in this case. It also excludes when we talk about negative infinity to infinity. Well, in some cases we actually will refer to that as a closed interval. We are specifically looking at closed intervals where we actually stop at a finite value on both sides. The other point here to note, maybe I should emphasize, so we have a closed interval, but we also have to be continuous. If, say, we were to try to instead look at 1 over x from negative 1 to 1, if we went all the way from negative 1 to 1, we would actually lose the ability to have an absolute minimum in that case. We'd have no absolute maximum and no absolute minimum. So the fact that we have that discontinuity at 0 is a problem. Our function wasn't continuous. We need both those two key pieces to guarantee that we have these absolute maximum minimums. Now, it is possible to have absolute maximum minimums otherwise. This is just a theorem that guarantees the existence of them in one particular case that is generally enough to be very useful. But most of our examples, we're going to be looking at closed intervals with continuous functions, because those are by far the easiest ones to work with. So let's motivate our process here by looking at an example. We're going to look at problem 22. Here we have f of x is equal to x squared minus 2x minus 3. And we are given the closed interval 0 to 1. So we're guaranteed, because, this is a quadratic, it is definitely continuous everywhere. And we're given a closed interval 0 to 1. So by the extreme value theorem, we are guaranteed that there is going to be an absolute maximum and there is going to be an absolute minimum. Our job now is just to find that. Now, where could that possibly be? Well, let's take a look at the graph of this. So we have x squared minus 2x minus 3. Of course, this shows the entirety of the function. We want to restrict our attention to between x equals 0 and x equals 1. Only the stuff between these two lines is relevant. You can even zoom in on this. We're looking at this section of our graph right here. Where's the highest point? Where is the lowest point? Well, we're going to have to think about two possibilities. One, we're going to have to look for possible relative extrema. And let's actually look at that first. If it has a relative extrema, that would be a potential candidate for being an absolute extrema. So we'll go ahead and do exactly what we were doing in the last video. We'll take the derivative. Hopefully you can see that the derivative here is 2x minus 2. When we set this equal to 0, obviously we don't have any critical points where it doesn't exist. If we set this equal to 0, we just get x equals 1. We have a critical point at 1. That could be an absolute maximum, that could be an absolute minimum, but we're guaranteed to have both of them. How can we have both an absolute maximum and an absolute minimum if we only have one particular point? Well, think about what we have here. Our relative extrema that we just got was 1 comma f of 1. It's actually 1 comma negative 4. That is this point here. And it seems reasonable that that is actually the lowest point on this section of our graph. What would be the highest point, though? It looks like it should be over here at 0, at x equals 0, with a y value of negative 3. What is special about that point? What's special is that that is an endpoint. The endpoints of our closed interval are actual possibilities. Whenever we do a problem involving the absolute maximum or absolute minimum, we actually do need to include the endpoints as possibilities. They maximum or minimum could occur at those endpoints. If it occurs in the middle somewhere, it's going to be a relative extrema. And in fact, in this case, one of our endpoints was our relative extrema. Now, we could make a number line at this point and identify that this is actually a relative minimum. Usually when it comes to finding absolute maximums and minimums, I like to make a chart, make a table. Make a table where I put all the x values I got from looking at both the endpoints and looking for those critical points, and I'll put them over here. And then I'll look at the y values, or the f of x values, for each of those. Now we've actually seen what those are. So at 1 we had a -4, and we can already see that at 0 we get a -3. Note that we're not plugging 0 and 1 into the derivative. We're plugging them specifically into the original function. That's very important. We're looking at the y values, not the y prime values. So at 0 we have a y value of -3. At 1 we have a y value of -4. And all we need to do now, because these are the only possible places where we can have an absolute maximum and absolute minimum, all we have to do is identify which one is bigger and which one is smaller. -3 is bigger than -4, so our absolute maximum is here. And -4 is the smallest, so the absolute minimum is here. Now let's do that without actually looking at the graph first on another problem. Let's look at problem 24. Here we have a function f of x is equal to x cubed minus 12x, specifically on the interval from 0 to 4. Again, we are going to first identify any critical points, and we're not going to identify them as relative maximums or relative minimums. We're just going to identify the critical points. That means we take the derivative of x cubed minus 12x. Well, here we get a 3x squared, then minus 12. If we set this equal to 0, essentially we get 3x squared equals 12, divide by 3, get x squared equals 4, or the x is either positive or -2. Then we're going to make a table where here I'm going to put my x values, specifically the endpoints. I need to include the endpoints, and I need to include my critical points. So my endpoints are 0 and 4. My critical points are -2 and 2, but do note that -2 is not in this interval. We don't care about -2. So we're only going to be looking at the critical point of 2. And then we'll evaluate our function at those three numbers. Essentially, we just plug 0, 2, and 4 into x cubed minus 12x and see what we get. When we plug in 0, of course we get 0. When we plug in 2, here we get 8 minus 24. It's actually a -16. When we plug in 4, get some bigger numbers. We get a 64 minus a 48. That is a positive 16. And what this means is that we look for our biggest value and we look for our smallest value. Our biggest value among 0, -16, and 16 is definitely just 16. So our absolute maximum is here. So we can say that f has an absolute maximum of 16 at x equals 4. What is the smallest value? Well, our smallest value is definitely the -16. So our function has an absolute minimum of -16 at x equals 2. We can go ahead and graph this just to show why that's true. So we have x cubed minus 12x. We get this thing here. Let's go ahead and scale this y-axis, so you can see a little bit better. I'll expand this out as well. We're looking specifically between x equals 0 and x equals 4. We're only looking at between these two lines. So there was a relative maximum over here at -2 because we found that critical point, but it's not relevant to this problem. We're only looking at this section of our graph. So at 0, it kind of is, you can almost say it's a relative maximum for this section, but it's not the highest or lowest point in here. There's definitely at 2 we're at a low point. It's actually at -16. And at 4, we're up here at our high point. The highest point, at least on this section of our graph. Let's do another problem. Let's go to problem 26. Here they're calling a function h, and they're using the variable t. It's not going to change what we do with it. It's t over t minus 2. Specifically on the interval from 3 to 5. We're looking for the absolute maximum, absolute minimum of this function on this closed interval. Now, there is a slight issue here. This function is not continuous on the entire real line. If we want to make sure that the extreme value theorem does guarantee that we do have a absolute maximum, absolute minimum, we need to make sure that it is continuous on this interval. So we want to identify whether or not this is where the domain of this function actually is. Well, of course, the only problem is if the bottom is 0, if t equals 2. And 2 is not in this domain. And it is not in this interval. So this function is in fact continuous from 3 to 5. So we are guaranteed that we do have a maximum and a minimum. And it's our duty now to find out what those are. Of course, we start off by taking the derivative. We're looking for critical points here. We're going to have to use the quotient rule. Remember, in the quotient rule, we take the derivative of the top times the bottom minus the top times the derivative of the bottom over that bottom squared. I can go ahead and actually simplify the top. Here, actually, we have a 1t and a minus 1t. Those actually cancel out. We're left with this -2 on top. So our derivative is actually relatively nice for what it could have been. And now we can think about what's happening with this derivative. Where is this derivative equal to 0? Well, if a fraction equals 0, then the numerator has to equal 0. But in this case, our numerator is -2. That's never equal to 0. So this can never equal 0. It's never equal to 0. So we don't have a critical point from setting it equal to 0. What about when the derivative doesn't exist? Well, it's only not going to exist when the denominator is equal to 0, and that's only going to be true when t equals 2. But t equals 2 is not an interval, and it's technically not even a critical point. It's a discontinuity. So really, t equals 2 is not relevant to what we're doing here. All we have are the two endpoints. And we'll go ahead and make a chart using those two endpoints. I mean, technically, we're just evaluating the function at the two endpoints and seeing which one's bigger. But I like the chart just to keep things organized. Now, when we plug in 3, we get 3 over 3 minus 2, which is 1. So we just get a 3. When we plug in 5, we get 5 on top and a 3 on the bottom. Now note here that we do have to compare 3 to 5 over 3. So one thing I'll say in these kind of problems, when we actually want to compare a bunch of values, and this is a simplified one where we only have two values to compare, it's possible to have a whole bunch of values to compare. To save us some effort here, we should probably just go ahead and use approximations. So 5/3 is approximately 1.67. Just use a calculator for that, because it's a lot easier to compare 3 to 1.67 than it was to compare to 5/3. And it's going to be even more important when we say compare, say, 3/4 versus square root of 2 over 2. These are two possible. These could come out as two possible places in our two possible values of a function, and we might have to compare them, and it's not obvious which one of these is bigger. It actually turns out the bigger one is 3/4. It's 0.75, whereas the square root of 2 over 2 is approximately 0.707. So 0.75 is a little bit bigger than that. But it's not obvious when we're left in these forms which one is the bigger and which one's the smaller. So this is definitely one case where I say using an approximation can be very beneficial. So back to the problem at hand, though. It's kind of just an aside. Which one of 3 and 1.67 is bigger? Well, it's definitely 3. So we actually have an absolute maximum of 3 at 3, and we have an absolute minimum of 5/3 at 5. I'm going to go ahead and graph this one as well. I'm going to have to use x's here, because if I just plugged in t, GeoGebra wouldn't know what to do with it. But we have h of x is equal to x over x minus 2. We have this curve here. Now keep in mind, we are specifically looking at between x equals 3 and x equals 5. We're only looking at this interval here, which means we're only focused on this part of our graph. And what we found is that we have an absolute maximum for this section of our graph at x equals 3, specifically at 3, 3. And then we have an absolute minimum at 5 of 5, 5/3, sorry. So that's the highest point, that's the lowest point, which is all we're really trying to identify. Next up is problem 30. Here our function is g of x, which is x squared minus 4 all to the 2/3 power. And we're looking at the interval from -6 to 3. So kind of a fun thing here. We're going to start the same way. We want to identify the critical points. You could question whether or not we actually are continuous on this interval, but remember the cube root, which is what the over 3 means. There's no problem with cube roots. This is actually continuous everywhere. But we're going to take the derivative. We're going to have to use the chain rule here. So we have an inside function of x squared minus 4. We have the outside function of this power. Differentiating that power gives us we get to bring down that 2/3. Then we reduce that 2/3 by 1 to get a -1/3. We still have that same inside function, but we also need to multiply by the derivative of the inside function. The derivative of x squared minus 4 is 2x. I'm going to go ahead and rewrite this derivative in a nicer form. First of all, I'm going to go ahead and combine the 2x with the 2. We're going to have a 4x on top. I'm still going to have that 3 on the bottom. And then I'm going to take this negative here, and I'm going to turn that into something on the bottom. In fact, we could go ahead and turn that into the cube root of x squared minus 4. Or we could leave it as x squared minus 4 to the 1/3 power on the bottom. Now we have two situations. First of all, when does this equal 0? Well, here's why I actually made this into a fraction. When we have a fraction equal to 0, that means that the numerator has to equal 0. We can actually ignore everything that's on the bottom. So that means that 4x equals 0, or that x equals 0. Where does the derivative not exist? Well, we're not going to get any place where it doesn't exist because of the cube root specifically, but only because of where the bottom equals 0. And I can ignore the 3 there. Basically, we're asking where is the cube root of x squared minus 4 equal to 0. Of course, the cube root there is not too important. The cube root is only 0 when the inside is 0, which means that x squared has to equal 4, or in other words, x is plus or minus 2. These are actually critical points because our function is defined on all real numbers. We can plug negative 2 and 2 into the original function. It's just that the derivative doesn't exist at those points. So we have 3 critical points. In fact, 0, negative 2, and 2 are all in this interval. We have a lot of things to look at. This is where making a table comes in really handy. So I take my endpoints, negative 6 and 3. Then I include all my critical points of negative 2, 0, and 2. And I'm going to have 5 different values that I'm going to compare. I do need to plug all 5 of these values into my original function. For negative 2 and 2, that's actually pretty simple. When I plug those in, we get 4 minus 4, so we just get 0 overall. So we actually get a 0 here and a 0 here. The other ones I'm actually going to have to approximate a little bit. For negative 6, we end up with a negative, we get a positive 36 minus 4, or basically 32 to the 2/3 power, which this is approximately 10.08. That's a lot easier to compare than 32 to the 2/3 power. That's a little hard to get your mind around how big that actually is. At 0, here we have 0 minus 4. Actually, the square here is actually going to get rid of the negative, so we don't have to worry about the negative. But this is going to be 4 to the 2/3 power. That's approximately 2.52. Finally, 3, we're going to have 9 minus 4, so we're going to have 5 to the 2/3 power, which is approximately 2.92. And so now we're going to identify between these 5 numbers, what is the biggest, what is the smallest? Well, the biggest one is definitely the 10.08. So we definitely have an absolute maximum here. The smallest, well, these three here are all positive. We're left with 0 and 0 as the smallest numbers. And it's okay that we have two different points where we have that same minimum value. These are both going to be absolute minimums. Because when we're saying absolute minimum, we're more concerned with what the value is. The absolute minimum of this function is 0. It just happens to be 0 at 2 different places. So it has an absolute minimum of 0 at negative 2 and 2. There's no issue with that. Once again, let's actually look at a graph of this function. Remember that our function was x squared minus 4 to the 2/3 power. We have this function here. And we're specifically looking at between x equals negative 6 and x equals 3. And actually, I can just drag it down. Here we go. So we have 5 different points. Remember, we have negative 6, comma, well, I'm just going to type f of negative 6. And it was 10.08. We have the negative 2, 0. We have the 0, comma, just going to type f of 0. We have 2, 0. And finally, we have 3, comma, f of 3. You can kind of see exactly. This will give us all 5 of the values if I had typed f of negative 2 and f of 2. But we have 5 relevant points. We have this point up here, which is definitely the highest point. That is where our absolute maximum does exist. Then we hit minimum points here at -2 and 2, but they have the same y values, so they're both absolute minimums. At C and E, at 0 and 3, those were definitely high points for the function on this interval. They just weren't the highest ones. But you can kind of see here where having a derivative that doesn't exist, there is actually in some ways a vertical tangent line here. It comes in and actually becomes very vertical just before hitting the x-axis, and then it becomes vertical again when it leaves. But the derivative doesn't exist at these 2 points because of the sharp corner that we have. But that doesn't mean that we can't have a relative minimum or relative maximum at those points. Let's look at one last problem. Problem 42. Here we're given the function f of x is equal to 8 minus 4x over x squared plus 1. And we're going to look on the interval 0 to infinity. Now, unfortunately here we are no longer working with a closed interval. Well, technically this is a closed interval, but it's not a closed interval where we stop at a finite value. Because that's not true, our extreme value theorem does not guarantee that we do actually have an absolute maximum and an absolute minimum. That doesn't mean we can't have them, but it doesn't guarantee them. So we're going to try our hand at this and see what we get, but just keep in mind that this is not going to be as straightforward as the previous problems, because we're not guaranteed any solution, and in fact it's going to affect how we actually handle the identifying whether or not something is actually an absolute maximum or absolute minimum. So let's see what happens. Well, of course, the first thing we're going to do is still look for those critical points. Let's look at the derivative of f. Of course, the 8 goes away. We're going to have to use the quotient rule for this part. I'm just going to leave the minus sign out in front and not worry about that for the moment. When I use the quotient rule, I take the derivative of the top. Derivative of 4x is just 4. I multiply that by the bottom. Then I subtract the top times the derivative of the bottom. Derivative of x squared plus 1 is 2x. Then we have the bottom squared. We'll go ahead and simplify this a little bit. So here we have a 4x squared. Actually, let me just write it all out. We have 4x squared plus 4, but then over here we have a minus. When we combine the 4 and the 2, we get a minus 8x squared. We can combine the 4x squared with the minus 8x squared to get a minus 4x squared. But then we have this minus sign out in front. I'm actually going to go ahead and distribute that on top. That's going to turn what we had of a minus 4x squared into a positive 4x squared, but it's also going to change this plus 4 to a minus 4. So my final derivative here is 4x squared minus 4 over x squared plus 1 squared. All right, where is this derivative equal to 0? Well, remember, the derivative only equals 0, or sorry, a fraction only equals 0 if the numerator equals 0. Basically, we're asking, where is 4x squared minus 4 equal to 0? Of course, we can go ahead and just move the 4 to the other side, divide by 4, and then take the square root. So at x equals plus or minus 1, we have a derivative of 0. On the other hand, if we want to see where the derivative doesn't exist, because x squared plus 1 is always a positive number, it's always at least 1. We're adding some positive number, or at least non-negative number, to 1. The bottom never equals 0, ever. So we only have critical points at 1 and negative 1. And in fact, we can ignore negative 1 because we're only concerned with the interval 0 to infinity. Negative 1 is not in that interval. So positive 1 is our only critical point that we want to look at. Now, unfortunately, that doesn't mean we can just go ahead and make a table, because the table only works nicely for closed intervals, because then we can go ahead and include those endpoints. Here we don't have an endpoint on the infinity side. So I'm going to have to go back to looking at a number line. So I'm going to make a number line. I'm going to go ahead and put 0 at the extreme end over here, because we don't want to even think about things lower than 0. And I'm going to put my critical point of 1 here. I'm going to go ahead and pick test points and see what's the sign of our derivative on these sections. So I guess from 0 to 1, I can go ahead and pick 1/2. If I go ahead and plug that into my derivative, specifically my derivative, I get, I'm not going to go through all this, but get something like negative 48 over 25. The important thing here is that we get a negative value. From 1 to infinity, I'll go ahead and pick 2. Again, plug that into here, and without getting into everything, I got 12 over 289. Of course, the point here is that it's a positive number, not what the value actually is. So we can kind of interpret from our number line what's going on here. We know that we started here at x equals 0. We decrease. So I guess we can kind of give a little bit of a sketch of what this looks like. It's a very rough sketch, but it will be helpful to identify what's going on here. So we start here at 0. We move down until we get here at 1, and then we move up. So it was decreasing, and then it was increasing. So we definitely have a relative minimum at 1. But we can kind of get an idea from our sketch here that has to be the absolute minimum. There's no way our graph can ever come back to lower values than it was at 1. It is continuous on this whole interval. In fact, this function is continuous everywhere. So this function is actually has an absolute minimum at 1. That doesn't mean we have an absolute maximum. You might think, well, maybe it's at 0. It could be an absolute maximum of 0. But we have no guarantee that over here, as x goes off to infinity, that it doesn't get higher than what we had at 0. And so, as it stands, from the techniques that we have from this section, we can't really say any more than we have an absolute minimum at 1. Now, from graphing, we can actually get a little bit of a better idea. If I go ahead and graph this, remember our function was 8 minus 4x over x squared plus 1. We get this function here. We can kind of see what's going on. At 0, we have the point 0.8. At 1 comma f of 1, which I guess was 1/6, as an absolute minimum of 6 at 1. At 8, it is kind of a high point, and as we go off to infinity, it's not clear whether or not we actually get higher than 8. It turns out here that we have a horizontal asymptote. If we look at the line y equals 8, this graph actually gets closer and closer to 8 as we go off to infinity, but it never quite actually reaches 8, at least over here. It reached 8 at 0. So actually, it does turn out in this particular case that we do actually have an absolute maximum of 8 at 0. It's just we didn't use the techniques of this section to be able to determine that part. We'll come back to asymptotes later on. I think in section 3.6, we'll discuss how we can find asymptotes for functions, and we'd be able to get a better idea of how this actually does have an absolute maximum at 8, or absolute maximum of 8 at 0. But at the moment, all we can really say is that we do have an absolute minimum at 1 of 6, And we can only get that idea from a kind of a rough sketch from our number line. We have to interpret what that number line is telling us. If we had a lot more critical points, this actually might be almost impossible to do. If say over here at 5 it suddenly became negative again, then I know that it has to go down again, and I don't know if it goes lower than it was at 1. So problem 42 really only worked because we only had one critical point in that interval. Don't expect to be able to take any function on any interval and be able to work with it. If we have a closed interval, then things are good. If we don't, then we have some issues. But as we can kind of see from here, that doesn't mean we can't get some information from it. So it's always worthwhile to actually at least take a look at it. Alright, but that's all I have for today. We'll continue talking about stuff like this in the next section. In fact, we're going to, you might remember we had a first derivative test. In our next section, we're actually going to talk about a second derivative test. So I'll see you there, and we'll learn all about that one.